This video covers common features that are shown in orthographic views. A lot of these features are just breeding grounds for mistakes. So we're going to cover this before we actually get into the how-to for this week's lesson. This particular part has several different um, bits of information, and we've got to be able to make sure that we treat these properly in an orthographic view. We have the part shown here in the upper right hand area of the slide with several terms pointing out in information. A lot of these things you're already familiar with. The fillet, for instance, the fillet is nothing more than a broken sharp corner or a 90-degree not really a 90 degree, it had to be 90 degrees, but basically it's a round between two surfaces that join. Now you have the fillet here and then the round out here. Technically they're two different things, but the truth being told, they are different. The fillet is an inside radius. The round is an outside radius. Now, when you're using the commands in AutoCAD, the command fillet is used for both fillets and rounds. And if you end up calling a round a fillet, I'm not going to fuss too bad about that. But the correct terminology for an inside radius is a fillet. For an outside radius is a round. And you can see here, top view, front view, and side view. The only time that you actually see the round here is in the top view. Now they've drawn an extra line here. Actually, this extra line here is for this chamfer. But you notice you only see the fillet in the front view here. The close cousin to the fillet is a chamfer. And basically, both of them are meant to break sharp corners. The chamfer still gives you a sharp corner, but it's not a sharp corner between what would have been two surfaces at 90 degrees from each other. The corners are smaller, therefore they're going to be less likely to chip and break, and that corner is going to be stronger. Most folks would have put a fillet in here anyway because the rounded corner of the fillet is going to be stronger than either one of them. Let's take a look at the top part of the part here. This is called a counterbore. Basically, it is a larger hole that has a set depth with a smaller hole starting at the bottom of the counterbore and continuing the rest of the way through the part. Let's look at the counterbore over here in the front view. You'll notice that the counterbore shows this larger diameter. And I look, one of the mistakes that students will make, and I'll bet even though I'm putting on this video, somebody's going to make this mistake. They will not continue the horizontal line for the bottom of the counterbore all the way across the part. It does not come down to the bottom of the counterbore, over to the smaller hole, and then down with nothing inside the smaller gap. This is the correct depiction for the counterbore. The counterbore is a hole that has a bottom, but it does not go all the way through the part. There is another hole that starts at the bottom of the counterbore. It's smaller in diameter, and it could continue part of the way into the part. It could continue all the way through. The purpose for the counterbore is for a fastener or a bolt to be placed in this part through this hole with the threaded portion of the bolt going through the part, and this recessed counterbore area being deep enough so that the entire head of the fastener fits below the top surface. That's the purpose of the counterbore. Notice what the counterbore looks like in the front view, in the side view, and in the top view. Another close cousin to the counterbore is the spot face. The spot face is here on this part. We look at the spot face here in the top view, and it doesn't look a lot different than the counterbore. As a matter of fact, they both use the same symbol, which is a three-sided rectangle, and you'll see that Let me look at this real quick. You will see that in exercises 6.12 and 6.13. How do we know that? Well, number one, what's different about them? Notice how shallow, now they don't even show a depth down here for the spot face. They should. The spot face is extremely shallow. We can look at it right here. We can see that the diameter that goes all the way through the part is 1.88 inches. The spot face has a diameter of 0.300. It has a depth of 0.01. It's very shallow. So what's the purpose of a spot face? The purpose of the spot face is to put a nice, smooth, flat surface on an otherwise bumpy surface, like maybe a cast iron surface. And this nice flat surface is just deep enough to make the entire surface of the spot face nice and flat, so that when we tighten a bolt up to hold the part onto whatever it's being bolted to, the bottom part of the head is not sitting on a bumpy, rough surface. It's sitting on a nice, smooth surface, which prevents or helps prevent the head from or the head of the bolt and the bolt itself from vibrating loose. The countersink is very similar as well, but when we look at the countersink in the front view, we see that the countersink has angled lines. It's a conical shape or a cone shaped. And the reason that we have this is some of our fasteners that we use, like sheet metal screws, are going to have a tapered head. They're not going to have a square bottom head like the fastener that goes with the counterbore. Most spot faces, most countersinks have an included angle of 82 degrees, and that's what you're going to use unless you're told different. Now, if you look at this designation right here, you have the diameter symbol, 0.188 through, that's the diameter of the through-going hole. This V is the symbol for countersink. The top of the countersink is 0.360 inches in diameter, and it comes down at an included angle of 90 degrees, which basically means both of these angled lines here in the front view are 45 degrees off of the horizontal surface that we have up here. Couple of other things. This whole area that sticks out in the front view and in the top view, this is a lug. Okay, lugs are basically protrusions, usually protrusions that are either there to hold features or to allow you to fasten the part that the lug is on to something else. We also see on this part something called a boss. Now the boss is this raised surface for this slot. Now what is this boss for? Well, sometimes we may end up with a lug like this one that really is too small. When I say too small, it's probably too thin to adequately support the part if I'm bolting this part to something else and running the fastener through this slot. So this boss sticks up a little bit. We can see right here the boss as it sticks up in the front view and in the side view. And it sticks up basically to provide a thicker area for the bolt to fasten up against, which makes the fastening stronger. A few other items. This particular cylindrical part has something called a knurl. The knurl is nothing more than a rough machine surface, and the knurl is there to provide a rough surface to help a user grip the part. Cylindrical parts oftentimes have a flange, and this flange is nothing more than a larger diameter, and you can see that this one has 4 bolt holes in it. Flanges are used to fasten this cylindrical part to another cylindrical part that also has a mating flange. This lighter green, more of a blue-green or a teal color, is a bushing. Bushings are used along with things like bearings and such to provide a softer material for this axis to rotate inside of. The bushing again allows for rotation while it supports and provides protection to this area that's inside of the bushing. So sometimes we'll have an area like this. You can see it really well over here on the side view. This narrowed down or necked down area is called a neck. Now that neck could be there for several reasons. Um, be anything from holding a snap ring fastener to some other sort of work holding device. And finally, we have a keyway, which is nothing more than a slot. This particular part probably turns and rotates another part. Well, how do you connect those two parts? Well, you put a key in here. It's a rectangular shaped key. Half of the key fits inside of this slot, and the other half of the key fits inside of a mating slot that is on the other part. Keys are used again to provide that connection so that as we turn this part, something else turns. But usually the keys are made out of a softer material so that if for whatever reason we've got enough power on this particular part here, that as it's being turned, if the other one gets stuck or seizes, we don't want anything important to break. So the keys are usually made out of a softer material so that they break before anything of greater importance breaks. Now, pay attention to these two slides. They're pictures right out of the textbook. Study them well, especially the way the bottom of a counter bore or a countersink looks. Because if you make these mistakes, it will cost you points on your drawings. So spend some time studying both of these drawings in your textbook.